Hello. Thank you so much to everybody who is currently signing on. We are just going to allow people to actually get signed in. So we're going to have a little bit of just a few minute wait to please grab your tea or coffee now, because once we start, we'll obviously jump into things. Hello, Ollie.
Hello.
Yes, how are you?
Good, good. How are you?
I'm good, thank you. Yeah.
Good.
Nice to be, I see you in the St. Helens office.
Another office of Enspec.
Yes, I know.
What's going to be happen here?
This one's expanding. Yeah, so you will have seen the big Manchester renovation that we did last year. And this year we've actually got a additional space next to us.
Oh.
So we're gonna break through and have a dedicated space for podcasts and webinars. Because this is obviously a boardroom. And we're also going to move all of our test facilities there so that we've got a bigger space.
From Manchester office to here.
From the Manchester office to here, yeah. So that there's more consultancy space in the Manchester office.
Nice.
But we can do all of our sort of product design and testing here. And then we're hoping,
design.
yeah, the sample design, yeah. And then we can have this be a bit of a training center for commercial teams and apprentices and interns and so it's exciting. So that'll be a big focus for next year.
Okay.
It'll probably take most of the year.
Interesting.
Yes. Yeah. I'm looking forward to this though. I know you worked really hard on this. How are you? Obviously we're gonna go into things, but what has been your most interesting learning so far?
In terms of the learnings, I can say a mixture of hydrogen stuffs and power quality stuffs. There is a very, I can say, a boundary between them. But here at Enspec, we are looking at the boundary from both point of views, from the both perspectives. And it's very interesting to me. Yeah.
Good.
Yeah.
No, I think a lot of interesting stuff has come out of it, and just how impactful it is. I think when we did the initial market research isn't even something that I fully understood at the time. It was an identified area. It was something that I knew we needed to be within. There was lots of research around it, but the more research that you do, it's what we've discussed here.
And now we can easily see the market expansion.
Yeah. Definitely. For those of you who have just signed on, excuse me, we are just allowing people to sort of get signed in and settled. So it'll just be a few more minutes. So, once we begin everything, we'll be straight into it. So please do grab your tea or coffee now, get settled, and we'll start in just a few minutes. Thank you very much. Are you looking forward to the Enspec Christmas party?
Yeah, of course.
Yeah.
Yeah, of course.
And,
it will be on next week.
Yes. Yeah. They're quite fun. They are quite fun.
It was great last year.
Yeah. Good.
I'm really looking forward to this year round.
They always we've over time we've got a little bit of a consistent structure where we always do outdoor activities. So there's always like a clay pigeon shooting
it was already perfect.
Yeah. But I know that this year we've rented out a castle, so it should be quite exciting.
First day or second day?
Both days. So
okay.
The night is at the castle, but we will sort of check in, do the outdoor activity, because that was the issue that we had, was that last year the actual do itself, the evening party, was such a success that some people did drop out of the outdoor activity the next day.
Yeah.
So we thought, well, we'll do the outdoor activity the first day this year, then we'll have the evening soiree, and then we'll do the walk.
For the team.
Yeah, good.
And especially for new graduates that joined recently.
Yeah.
You're
Well,
familiar with the team?
it's that's it, is because we're spread across 3 offices. There
Yeah,
aren't
yeah.
that many times where we all actually get to be together.
This is the time. Yeah.
This is the time, yeah. So we do the Christmas one, and then we have like a mid-year meetup where we try and do it as well.
Okay.
Excellent. So I think everybody is signed in. So welcome everyone. Thank you so much for joining us today on today's webinar, specifically on hydrogen electrolyzers, challenges and capabilities. Now, no doubt this is going to be one session of many. We are just past the halfway mark with Dr. MohamadAli's research, which we are going to go into today, specifically with regard to hydrogen electrolyzers and integration into the grid. Should I do this? There we go. So I'm Mara Rastall. I'm CEO of Enspec Power. I'll be explaining a bit more about Enspec, what we do on a day-to-day basis, but also why we've decided to invest in hydrogen research. But first, I want to introduce my colleague, our KTP associate and power system analyst, Dr. MohamadAli Amini. Welcome, Ali. Thank you very much for joining me today.
Thank you, Mara, and hello, everyone. Thanks for joining this webinar. I'm Ali, power system analyst, and I do power system studies working at Enspec Power, and more specifically, I'm working on a project on hydrogen technologies and its integration to the grid. As we are power system engineers, we look at the problem from power system point of view and more specifically power quality point of view. I'm working as a partnership with Manchester Metropolitan University, and I'm so glad to be here. Thank you.
Thank you very much. Just to make everyone aware, we are accepting questions throughout the webinar. It is a closed chat, but it's moderated, so you are welcome to drop any questions into the chat. We'll be taking note of them. But if you have a question following the webinar, or if you would prefer to email, please do send all questions to events@enspecpower.com. If we don't have an opportunity to get to questions today during this session, because we do want to focus on the bulk of the content, we'll be following up individually with answers. And we'll also be doing a roundup email for all of you who have attended with regard to what we feel are the top questions and their answers. Perfect. So as an overview of what we will be discussing, I'm going to give a little bit of an intro of Enspec, as I mentioned, and really looking at why we are well placed to do this KTP and contribute this research, particularly as hydrogen technology grows. But also, more about the bread and butter of what we do. I'm then going to pass over to Ali to go through the bulk of the presentation, specifically looking at different types of electrolyzer technology, the different considerations, but also opportunities that we have from a grid connection and integration perspective. We'll be looking at a market snapshot in terms of hydrogen production's growth. But one thing to note in this presentation, because I know it's a very common conversation, particularly with regard to hydrogen in the mainstream media, we will not be discussing hydrogen's end case use. When we were looking at hydrogen as a market, we are well aware that it is a commodity already in existence, and that there is a very large amount of gray and brown hydrogen already in existence that will need to be replaced with a sustainable source. And so that was the basis for our interest. And again, the bulk of the presentation will focus on integration considerations and how it impacts the grid. Whether or not it will be used in a residential sense isn't really our concern. Yes, brilliant. So to tell you a bit about Enspec Power, we are a 25-year-old electrical engineering firm. We specialize in power quality and grid connection. 80% of our core client base are large energy generators, particularly inverter-based technology, so big wind farms, solar farms, hydro plants. In its most holistic form, if you had a brand new wind farm, it would need to get a grid connection agreement in order to operate. To do that, it needs lots of pieces of criteria. Power quality is one of them. So we are very niche within the supply chain, but we're global experts in what we do. And we help in one of three main ways. So we have a very developed and technically astute consultancy department who focus on power system studies. Studies and simulations to show whether or not a site does in fact meet grid code requirement. If they do, then great. We are able to submit our studies with an application in order to get the grid connection agreement. If they don't, then we can design, manufacture, and commission what are classed as mitigating solutions. Things like harmonic filtration, reactive compensation, power factor correction, point on light switching. The other 20% of our core client base are large energy users, data centers, hospitals, advanced manufacturing sites, zoos. In the same sense that power isn't always generated in a usable form, the more it's drawn, it can have an altering effect. And this can lead to safety issues, operational issues, things like flickering lights, motors that randomly trip, things that randomly go boom. So we can actually take a step back and do a what's called a power quality survey, where we connect an analyzer to an electrical system. It takes a series of electrical readings in the hopes that it catches an event. This data then goes to our power system study team so that they know what studies to run, so that we then know what equipment to manufacture to solve the issue. We also commission and maintain all of our own equipment, which is the site services branch of our business. We are a trusted name within the industry, and we have a global presence. Now, hydrogen has been on my radar for several years as an emerging market, and it's one that came about through the discussion with our power system engineers, because you could see very large wind farm projects come in that had very developed study packages that need to be completed, and they ran without a hitch. There was really no sort of operational stress to our team, because everybody knew what to expect. People knew what deadlines they needed to adhere to, and what needed to be submitted. And this was a stark contrast to what were lower capital cost industries, things like solar and BESS, where we would have clients call us with what I would describe to be panic buttons, people who didn't necessarily know the process, had an energization date within 2 weeks, and it needed power system studies now, which, because of our team size and because of how we try to operate as a business, we would aim to be amenable, and we would try and help them, much to the stress of our 4 power system studies teams. But when you look at hydrogen, and you look at its expansion, we know that there are no utility scale facilities currently in operation, particularly not within the UK, but even globally, it's still a very emerging market, particularly, as we will discuss, for yellow and green hydrogen sources. And therefore, there isn't a lot of expectation with regard to what regulations will be in place and what types of processes people need to adhere to. This was the basis for the presentation of the KTP idea, which, as Ali has mentioned, we are doing with the Manchester Metropolitan University. It's a really exciting piece. Ali is 1.5 years in to a 2.5-year program. And really the intention is to position ourselves in the hydrogen market as we position ourselves for all of the other industries that we sit within, but is as a knowledge partner to be able to support and guide our clients, no matter the journey that they're on, to ensure that they are as geared up with the knowledge that they need as possible. And it's very exciting. And, you know, I think unexpectedly, when we looked at this KTP, we really anticipated that it was going to be purely based off of simulation. and that it was, we were going to be looking at comparing technologies. And what we didn't expect is that we were going to have so many inquiries within the pipeline, and that we were having active projects that we're working on now to help guide the research. So it's not just a market that's emerging and forecasted and on the horizon, it's a market that's here. So without further ado, I would like to hand over to Ali to lead our presentation on his research so far. Thank you very much.
Thank you, Mara, for the introduction. Yes, in this presentation, we will discuss about hydrogen technologies, and as this is the first session of a series of webinars, we will discuss more about the fundamentals and any challenges that may arise during the hydrogen production from the power quality point of view, and also the capabilities that they might have to support the grid. So let's start with the basics. When you hear about hydrogen production, you will hear about different colors that are representative of different production process. Depend on the source of the energy and also depend on the process. The hydrogen production could be categorized as different colors. For example, the gray one, which uses the natural gas as a source of energy and produces the hydrogen through the forming process. So the main outcome will be hydrogen, but carbon dioxide will be the waste in this process. The advanced level of the gray hydrogen production is the blue hydrogen production, using the same source of energy, natural gas, and the same process, reforming, but it is equipped with carbon capture and storage system. So the produced carbon dioxide will be stored appropriately. In addition to that, we have hydrogen electrolysers, which uses the electricity to produce hydrogen. Depend on the source of the energy, they could be categorized as pink, yellow, or green. The source of energy could be nuclear, solar, or grid, or renewables. The main outcome will be hydrogen.
I think within the mainstream media, we do hear about green and yellow hydrogen more than probably any other sources, particularly as an emerging market. But why are they so interesting from a power systems perspective?
Yeah, this is a very good question. As we can see here on this slide, the hydrogen production in green or yellow doesn't have any waste compared to the other types of hydrogen production. And also the source of the energy is the renewable energy, so no carbon dioxide is there. That's why, in short answer, that's why we more hear about green and yellow hydrogen production. Okay, let's get into the more detail about green and yellow hydrogen production and why it does matter from power system perspective. As I said, hydrogen electrolysers uses electricity to produce hydrogen, so they need to be integrated to the grid. And in order to integrate a hydrogen electrolyser to the grid, as they are DC loads, there is a need to have a power electronic interface. This power conversion system or power electronic interface will bring some advantages in terms of the operation for hydrogen electrolysers. If we would like to have, if we want to have a look at the aspects of integration of a hydrogen electrolyser to the grid, for the first positive aspect, we can say as the hydrogen electrolysers are large-scale loads, they are controllable. So they could provide some services to the grid. For example, from the power load balance, they could provide balancing service to the grid, and for the electricity grid with high penetration of renewable energy sources with intermittent nature, hydrogen electrolysers could support the grid in terms of the balancing. In addition to that, as a hydrogen electrolyzer are flexible loads, they could also help the grids to reshape the load pattern with different functionalities like load shifting or any flexibility.
It's really interesting to hear about all the positives with, you know, lots of perspectives in place, but what about the negatives? What about the challenges?
Yeah, very good question. In addition to the positive aspects, there might be some challenges because the hydrogen electrolyzers are integrated to the grid through a power electronic interface. Of course, there would be some challenges in terms of, for example, harmonics, reactive power issue, or flicker issue, are the main power quality issues that it may arise in consequence of an integration of a hydrogen electrolyzer plant. Okay, let's have a look at the hydrogen electrolyzer technologies available in the market, in the industry. And more specifically, this is about the stack technologies. As of now, we have 3 types of stack technologies available in the industry, mainly alkaline water electrolyzer, proton exchange membrane, and solid oxide electrolyzer. Let's have a look in detail and compare them against each other. At the heart of a hydrogen electrolyzer plant is the stack, which forms from multiple cells, and as I mentioned, it is a DC load. So in order to supply a DC load, the AC voltage of the grid needs to be stepped down to an appropriate AC voltage, and then rectifies it to a DC voltage for supporting the electrolyzer. In addition to that, plant facilities, in order to ensure the operation of the system, operation of the plant, are needed.
And what implications does this have on the power system?
Okay, this is a very good question. As the hydrogen electrolyzers, as I mentioned, are large-scale loads, and they are integrated to the grid through a power electronic interface. In addition to the major component, like the amount of demand that they need to be drawn from the grid, or the, for example, the reactive power that they need to be drawn from the grid. Other implications could be from power quality point of view, like harmonics or flicker issue that needs to be considered after integration of the hydrogen electrolyzer plant.
I know we were discussing earlier and kind of looking at a probably more layman's comparison, but I really liked the analogy that you used, which is if you plug a computer charger into an office building and the lights flicker, you know, it has impact. It has impacts on my colleagues, and it, you know, we know that there is a regulation in place for what the tolerance is, but it's really a symptom of what has gone wrong between the charger and integrating into the electrical network. And if you then kind of compare that to a hydrogen electrolyzer and it connecting into the grid, that the impact can be quite phenomenal. And that it doesn't just impact, you know, the area at which it's connected, but can have a more regional, larger scale impact along the grid, which, you know, is because it's so large itself that you amplify the symptom from the fact that it's now a much bigger facility. So it's something that really needs to be considered as part of the as part of the, what's the word I'm looking for, but the design of the electrolyzer and ensuring that it does in fact meet with the appropriate requirements as it's connected, because the impact can be quite catastrophic.
Yeah. This is a very simple example of what's happening when we have a large scale hydrogen electrolyzer going to integrate to the grid. Yeah, there might be different issues at the point of connection. And the issues might be locally, for example, the harmonic issue or voltage issue are local phenomena. But in addition to that, there might be some grid-wide issues. For example, when we have a large-scale load connected to the grid, there might be some mismatch between the load and generation. So the frequency issue is a grid-wide issue. So these issues needs to be investigated before connecting a large-scale plant to the grid. We will explore this in the rest of the webinar. Okay, in terms of the electrolyzer stack technologies, as I mentioned, there are three types, dominant types. In the industry, alkaline water electrolyzer is the mature one, which was used in the industry for hydrogen production for many years. As you can see here in this slide, the alkaline water electrolyzers are good for large-scale applications. They have the minimum capital investment index compared to the other types. In addition to alkaline water electrolyzer, we have the proton exchange membrane or PEM, which is the main advantage of the PEM type is about flexibility. We can see the response time for PEM type is in the range of milliseconds, while the response time for alkaline water electrolyzer is in the range of seconds. In addition to that, we have the ramp rate index, which is around 100% per second for PEM type, which makes it more flexible than the alkaline water electrolyzer, which has a ramp rate in the range of maximum 25% per second. In addition to these two, we have solid oxide electrolyzers that operates in a higher temperature compared to the other types, and this type is more applicable for the locations where the heat is available.
And so what are the advantages, understanding that it's sort of new to market, still in R&D, what are the advantages of solid oxide electrolyzers?
As the advantages of solid oxide electrolyzers, we can mention that they are very good for large scale applications. And in addition to that, it is about efficiency. We can see the efficiency of solid oxide electrolyzers are in the range of around 90% and is higher than the other types for PEM and alkaline water electrolyzer, but they are at R&D stage and not commercialized or not at the mature stages. Okay, let's have a look at the hydrogen electrolyzers as an energy storage and compare it to other types like batteries and pumped hydro. If we produce hydrogen using hydrogen electrolyzers, the produced hydrogen could be used directly by the user, could be transported to the downstream hydrogen users, or it could be stored in different ways. For example, they could be stored in tank or underground caverns. So if we produce hydrogen using hydrogen electrolyzers and using the renewable energy sources or electricity through hydrogen electrolyzers and store it in a tank, and then if needed, we can reconvert it to electricity using fuel cell. But this round trip does not have a much high efficiency for hydrogen. The round trip efficiency for hydrogen is in the range of 20 to 40%, but this round trip efficiency for batteries is about 80 to 90%, which is quite higher than the hydrogen, and also for pumped hydro, which is in the range of 70 to 85%. But this is not the only application of hydrogen electrolyzers. Hydrogen electrolyzers could have different applications in terms of the time scales. They could have the applications in the range of seconds to minute, for example, for voltage and frequency regulations and providing the voltage and frequency support services to the grid. In addition to that, they could have some applications in the range of hours, in the time scale of hours for load leveling or peak shavings, or for longer term applications in the range of months for energy management and longer term applications. Let's have a look at the market snapshot globally and more specifically on UK market. If we have a look at the hydrogen electrolyzer plants going to commission before 2020 and then compare it to hydrogen electrolyzer plants going to commission before 2025 and before 2030, we can easily see the massive expansion in hydrogen electrolyzer plants going to install in a couple of years. And if we compare this massive expansion with other types of hydrogen production, which is fossil fuels plus carbon capture system, which is the blue hydrogen production, we can easily see the attraction to the green hydrogen production, green or yellow hydrogen production. In order to meet that expansion, the hydrogen electrolyzer manufacturer needs to be also expand. For example, the giga-scale hydrogen electrolyzer manufacturers announce an increase planned to their production capacity. For example, here in the UK, ITM Power announced that they have a plan to increase the hydrogen electrolyzer production capacity from 1 gigawatt per year to 5 gigawatt per year. And also we have this expansion plan for other giga-scale hydrogen electrolyzer manufacturer all around the world. If we look at this expansion in a big picture, we can easily see the cumulative hydrogen production capacity all around the world, which will be increased by 2030. More specifically on UK market, the UK government announced that the hydrogen demand will form around 20 to 35% of the total UK energy demand by 2050. And in order to meet that, the hydrogen production capacity here in the UK needs to be increased. We can see on the right-hand side diagram that the hydrogen production capacity will also increase, and the main portion of this expansion will be hydrogen electrolyzers. In terms of the UK project, I'm going to mention some projects here. We've got in the UK Kintore project in the range of 3 gigawatt, which will be operational by 2030s, a very large scale hydrogen production site. In addition to that, we've got the Dolphin one in the range of 4 gigawatt, which will be operational by 2037 in the northeast. And also we have Tees Green with the size of 7.5 megawatt, which will be operational next year, and also the North Fleet project, 16 megawatt, which will be operational in a couple of years.
Exciting to see some familiar names.
Yeah. Yes. Okay, let's have a look at the power system integration of hydrogen electrolyzer plants capabilities and any technical challenges that may arise during the integration. Hydrogen electrolyzers are mainly to produce hydrogen for downstream hydrogen users. In addition to their main obligations, they could provide some services back to the grid. As I mentioned before, the main service could be the load balancing for high penetration of renewable energy sources with intermittent natures, and also in addition to that, hydrogen electrolyzers could provide some voltage support services through injecting or absorbing reactive power In addition, they could also provide some harmonic support to mitigation support at the point of connection, and more ideally, they are also capable of providing frequency support to the grid and by participating in appropriate ancillary service markets. In addition to the capabilities, there are some challenges that may arise at the point of connection of a hydrogen electrolyzer plant. Mainly as they are large-scale loads, as we have seen in previous slides. Large-scale variable loads, they could cause some issues at the point of connection and depend on their fault right-through characteristics. The protection schemes at the point of connection might need some modifications. In addition to that, from power quality point of view, flicker and harmonics will be the main issue at the point of connection. And in addition to these challenges, the hydrogen electrolyzers have some obligations to support the downstream hydrogen users. If we have a look at the power converter station in more detail, the power converter station could have different configurations, from the simplest configuration, 6 poles, 12 poles, to the most advanced version of power converters, like active front-end conversion system. The basic systems like 6 poles and 12 poles are more likely to need AC harmonic filters at the AC side, but this is less likely to be the case for active front-end converter configurations. In terms of the power system studies, the required power system studies and modeling approach, we can say in order to study a hydrogen electrolyzer plant, and when it comes to the developing a model for the studies, that model needs to have 2 different layers. The first layer is about the electrical components, like the grid model, the transformer, or the rectifier itself. And the second layer will encompass the electrolyzer and downstream hydrogen flow rate. Of course, the first layer will introduce some fast dynamics in the range of millisecond to second to the model, while the second layer will introduce some dynamics, slower dynamics, in the range of seconds to minutes to the model. In addition to that, the first layer will define and introduce harmonic and fault contribution at the point of connection, while the second layer will introduce some limits to the model. For example, the minimum load limit or the ramp limit, as I mentioned previously. In terms of the power system studies, we can say at the earliest stage of the study, feasibility study and studies for the grid integration, and the steady state power flow, of course, will be needed. Fault level check and capacity study could be done at the very earliest stage. After that, at the middle stage, protection coordination study, relay settings, and fault right-through requirements are essential. And before the final design, if required, dynamic and EMT stability studies, frequency response studies, and harmonic and flicker from power quality point of view could be done. In terms of the modeling tips, in order to develop an appropriate model for the study, that model needs to encompass different components. For example, an equivalent model for the power grid needs to consider the fault level, background distortion, grid impedance for any probable resonance check, for any probable resonance, from the controller itself, active and reactive control, and also current limits needs to be considered. For the electrolyzer itself, stack dynamics, stack constraint, and minimum load and ramp rate needs to be considered in the model. And for and also the downstream hydrogen flow rate needs to be considered in the model.
I know data is so important for accuracy. Where do we get this data from?
This is a very good question. We always have a discussion with the clients to advise them how to get and how to collect these data. Depend on the components and the model they are looking for that data, they need to refer to different authorities for collecting this data. For example, for the grid equivalent model, they need to refer to the grid operator, depend on the connection point, TNO or TSO, and also for the components like transformer, controller, and electrolyzer itself, they need to refer to the vendors, for example, transformer vendors, controller vendors, and electrolyzer vendors to collect this data. And for the next session of the webinar, we will discuss about technical mitigations and control strategies and also case studies that we have done here at Enspec in terms of the hydrogen electrolyzers. Thank you, everyone, for
Yes,
your time.
Thank you so much. Thank you, Ali, for your presentation and for your hard work and the topic so far. We really do encourage everyone to follow us on LinkedIn. It's where we're most active and vocal and where we share industry insights, thought leadership, case studies, company news, sustainability reports, and where we will be updating on future webinars. As mentioned previously, if you do have any questions following this session, please do feel free to send us an email to events@enspecpower.com, where we will be following up individually, and we can include it in our roundup email, which we will submit to all the attendees today. I just want to say again, a massive, massive thank you to Ali. Obviously, this is, one of, I'm sure, a multi-part webinar series, but it's been a lot of hard work, a year and a half. Yeah. We've got another year to go with, I'm sure, more work on the horizon.
Yeah, of course. Yeah, we try to keep this on the fundamentals and basic to get everyone familiar with what's happening in this industry. And then in the next session, we will discuss more technically about the challenges and practical cases that we have done here at Enspec.
That's it, exactly. Foundational knowledge that we can build from. I also wanted to give a massive thank you to our marketing team who worked so hard to pull this together. It's a skill within itself to ensure technical clarity and that we could include enough information and visuals so that this would be as understandable as possible to as many people as possible. So thank you so much, everyone, for attending, and really hope to see you on the next one. Thank you.
Thank you. Hope to see you later.